Welcome back to our third session. So we are looking at this Schumpeterian model. Where is it? Okay. So as we said earlier, innovation is going to be a stochastic event. Okay. So it could be successful or unsuccessful, right? So if innovation is successful, productivity of the machine in period T will be greater than productivity used in period T minus 1. Okay, productivity of the machine used in T minus 1. So gamma is a parameter that is greater than 1. So in fact, we see that it is an important parameter that determines the growth rate. So it is the step size, right? So in the beginning of T, the targeted productivity is then this, right? So there is this targeted productivity. We want to invent, the research sector aims to invent a particular machine, a particular version of the intermediate good that has this level of productivity. And for this, the research expenditure is again denoted by R, and it is again in terms of the final good. All right, so we make a huge simplifying assumption here. So there is no engineers, there's no workers in the research sector. Once again, the entrepreneur has to spend some money that is accounted in terms of the final good. Okay. Now, if it is a stochastic event, we have to talk about the probability of success, right? Now, the probability of success is denoted by mu, okay? And mu will depend on two things. First, it depends on total amount you spend, which is R. So if R is getting larger and larger, the probability of success is getting larger. But there is also this this fishing out effect. So if you target a very high productivity, you have to spend more, right? So it is more difficult to be successful if you want to create something very productive. Okay, so probability of success depends on this normalized research expenditure. So research expenditure normalized with targeted productivity. Okay, and we assume here a very simple functional form, which is a power function, basically lambda times n to the sigma. So n is the normalized research expenditure, lambda is greater than 0. Once again, it is the research productivity, and sigma is decreasing returns parameter, right? Sigma is between 0 and 1. Guess what? Once you increase the research spending, you increase the probability of success, but the pace of increase decreases, right? So there is decreasing returns in the research technology. Now, let me remind you one thing. The profit depends on AT, right? Because profit depends on the total units of machine that you're going to produce, and that total depends on productivity. So your targeted profit also depends on your targeted productivity. Okay? Now, what is the expected profit for the entrepreneur? Remember, entrepreneur is just some outside agent, okay, who tries to disrupt the monopoly of the incumbent firm. Okay, so the expected profit can be written in this way, right? If I am successful, I'm gonna obtain that profit, IT star. We're gonna see how we can write it in a moment. If I become unsuccessful, I earn nothing, obviously, right? Because I don't have the new blueprint. But in any case, I spend the amount RT. Okay. So the expected profit from research is that. Now, what is that profit equal to? Well, there's this parameter that depends on alpha. If you do the math from this, if you do the math here, if you put x back into the profit, okay, so there's this x you have, right? If you put this back into the profit function, you obtain profit as a function of AT and L. So the targeted productivity pi star would be this pi parameter times AT star times L. Okay, then the problem becomes choosing R. Okay, choosing R to maximize this, right? Because this term basically cancels out, right? Oops. So this term right here basically cancels out, and you have mu here and the profit here minus R. And realize that we can write this in this particular way. How? Well, A star is positive, right? So I can actually divide the profit function with AT star so that the problem becomes this. Okay. And there's a very nice solution, very simple, nice solution in terms of normalized research expenditure. Okay, so if you take the derivative and equate it to 0, this is a very simple, convex optimization problem. So that's the optimal normalized spending on research. Okay, and as you see, it is fixed. Now that will be very important. Okay, that will be very, very important, especially in the multi-sector model, because that one sector model is not good because it is too restrictive, right? But if that's the case, then success probability is also fixed, right? Because success probability basically depends on n, as you see. So if you know n, and you know n as a function of parameters and some exogenous variable L, so the success probability is mu, and it is also fixed. Now, how can we understand the growth of productivity within such a framework? Well, the growth rate now is defined in this way, right? AT minus 1 divided by AT minus 1. But be careful, it is stochastic, right? Why it is stochastic? Because in some periods there is success, in some other periods there are failures. Okay, so in that particular sense, we can only talk about expected growth rate. Okay, because in some periods growth rate will be 0, as in here, when there is failure. Okay, and in some other periods when there is success, the growth rate is gamma minus 1. Okay, so the expected growth rate is then equal to this, right? Success probability times the step size. Okay, so there's a typo, so there must be gamma minus 1 here, obviously, right? So if we look at the time path of the growth rate, we can look at the time path of the growth rate. In some periods it is 0, as you see, these are the failure periods, and in some other period it is gamma minus 1. Okay, so on average, growth rate is expected to be depending on the research intensity mu, basically, right? How successful your research technology is, and the step size. Okay. Now, once again, look at the expected growth rate. Expected growth rate is once again depends on L, right? So if L is getting larger, then expected growth rate is larger. And also, you can still introduce policy, right, as we did earlier. So you can actually write a model with research subsidies. So there is phi n times pi t star, right, minus nt. So you may want to subsidize research. Okay, and if you do that, optimal NT increases with the subsidy rate. You can also introduce public spending on research expenditure. You can also tell me that there is a particular budget constraint. So you can do all this policy stuff again. And also, as I said, this derivative is positive, and it is about the scale effects that we're going to discuss next week. But the other problem with this model is that it has only one machine, right? So the production function is like this. And this is too restrictive, right? Having only one machine. Now we're going to look at a version with more than one machine. Now let me show you one thing as well. So if this is the characterization of the growth rate, so it is like this, right? So there are some unsuccessful episodes, and there are some successes. Okay, so that's the growth rate for any team. Well, in reality, we do not. In reality, my friends, we do not observe such shifts. Okay, we do not observe such shifts. We do, of course, observe some fluctuations, but it is like this. Okay, so it is not near zero for advanced capitalist economies. Okay, so the multi-sectoral version will correct for this as well, as we're going to see now. So let me once again go back to my PDF and show you the multi-sectoral version. Okay, this one will be very similar. The only difference will be there will be more than one sector, right? So now intermediate inputs are located within the unit interval. Okay, they are located within the unit interval, and this is the final sector production function. Okay, now AIT is of course different across these machines, right? Across these intermediate inputs, because remember the productivity distribution that I showed you earlier. So we write it in this way. Then we again take the derivatives to find the inverse demand. And we again find the profit function of monopolist I. Okay. So all of this is the same. So we solve it. The solution of the monopolist problem is the same. Okay. Now it depends on that particular machine's productivity, of course. That part is also the same. Okay, so in each sector, the normalized optimal research expenditure is given by this. Okay. But now, in the case of growth, we see a totally different thing, right? Why? Well, some sectors will be successful, right? Some sectors will be successful, and some other sectors will be unsuccessful. Now, what's the good side of it? Well, successful ones will recover, will cover for the unsuccessful ones. Okay, so if you are looking at the average productivity defined in this way, right? The growth rate of average productivity depends on what? It depends on the growth rate of, so it depends on the productivity of successful sectors and the productivity of unsuccessful ones, right? So this is also an average, of course. This is also an average. The nice thing about this is that there is what we call the law of large numbers, right? And since this is constant, okay, since the research success probability mu is constant, we can execute the law of large numbers and say, well, the ex-ante probability of success would give you the fraction of sectors that are ex-post successful. Okay, so this is called the Borel version of law of large numbers. So you may have heard it. The notion is this. So the notion is this. I'm gonna show you that. It's called Borel's version of the law of large numbers. Okay, so there is an event. Okay, so that event has fixed probability for any time and any entrepreneur, and entrepreneurs are located within this interval. So what is mu? Mu is ex-ante probability of success. According to this law, mu is in the meantime ex-post fraction of successful sectors. Okay, you can try it in Excel. Suppose that you have 10,000 firms. Okay, each firm has a success probability of, let's say, 20%. Okay, so you can run a Bernoulli event, right? So each sector's innovation is a Bernoulli event. Either there is a success or there's a failure. Then you do that for each of the 10,000 firms. And if you count the successful sectors, the total number will be very close to mu times 10,000. Okay. So that's the idea of law of large numbers. And the good thing about this is that, again, we have a particularly smooth growth rate, right? Now the average growth rate, if we are interested in average, the average itself is a weighted average of the average productivity in successful sectors and the average productivity in unsuccessful sectors. So what is the average productivity in successful sectors? It is gamma times AT minus 1. What is the average productivity in unsuccessful sectors? It is AT minus 1, right? Again, law of large numbers. Then the growth rate is no longer stochastic. Okay? The growth rate is no longer stochastic. We are not putting all of our eggs into a single basket, right? We have many baskets, so we diversify the risk at the economy level. Okay, have you ever heard risk diversification? So that is exactly what it is. We diversify the risk because many different sectors would try innovation. In many different sectors, since many of them try innovation, some of the successful ones cover the stagnation of productivity in unsuccessful sectors. So the average growth rate is the growth rate of average productivity is not stochastic. Okay, and it is the same, right? Mu is the same. Mu is the same. Depending on this, gamma is the same, so you have the growth. Okay. So once again, you can put policy into multi-sectoral framework. You may target different sectors, right? Suppose that some sectors. So there are many nice modeling tactics here. So suppose that. Oh, by the way, I will show you how we can actually write a model with both vertical and horizontal innovation. Okay, I'm going to show you that. So we're going to study models where AIT grows and I grows, right? So there's horizontal innovation and there's vertical innovation. So suppose that I have the firms, okay, located, or the industries or the sectors, and let's say we rank them in terms of their existing productivity levels. Okay, so we rank these firms according to their productivity levels, and I'm interested in some particular level of productivity, okay, and I want to I want to support research in this very successful, in this very productive segment of the economy. Okay, so how can I do that? Well, their problem will look like this, right? Now I want to give subsidy to them so that
you didn't share. You didn't share.
Oh, I'm sorry. You should have said it earlier. I'm sorry. Okay. Here is your screen. Okay. Sorry. So I was talking about the vertical and horizontal. So we're gonna look at models like this. But for now, let's suppose that we have this setup, right? So there are M firms. So how do you use such a model for policy? That's I'm showing you. So you may have some priority sectors. Okay, suppose that some sectors are already very productive and you want to increase you want to support their vertical innovation even more to make them, let's say, innovation champions of the world. Okay, so you can do it. You can have targeted subsidies, okay, that are given only to these firms. Okay, let's say MBAR. Okay, so for firms, their optimal level of R&D spending depends on S. For other firms, doesn't depend on subsidies. Okay, so you may once you have the microeconomics, so that's the nice thing about the general equilibrium models. So once you have the decision makers in the model and their objective functions and in their constraints, you can extend the model from different directions. Obviously, I mean, you are not doing that for just the sake of extension. You have a research question, you want to target that research question, you want to answer that particular research question, but you can use models. And to me, maybe it's because I always studied such models, but general equilibrium models allow you to understand how you can extend a simple model into a more realistic and more complicated one. Okay, so let me pause here. That's all I have actually for today. Next week on Wednesday, we're gonna continue with I think we're gonna look at the scale effects, just check the syllabus. So in the mid-90s, there was this important debate among economic theorists on why these first-generation Schumpeterian models are not making sense in a particular dimension, on some particular topics. So we're going to look at that debate, and we see how second-generation Schumpeterian models actually resolved that debate. So now the floor is yours. If you have questions, comments, we can cover them.
Sorry, what is the pros and cons of the Schumpeterian models actually in the real life?
Well, as I said earlier, no theory, including, superstring theory in physics or, any other theory you may imagine, none of them is entirely realistic, right? Now, in economics, of course, we have many unrealistic models, and maybe some of them are, too simple and too abstract. The nice thing about the Schumpeterian models is that we can understand the origins of technological progress in a detailed manner, right? Because we give these people some purposes. We give these people some resources. We give these people some constraints. And we tell them, okay, so we ask ourselves, okay, how can we determine the laws of motion for technology? Okay. Here, of course, we take as given, right? We take the capitalist accumulation system as given. So there's private ownership, economic rights such as contracting rights, etc. So we take all this institutional setup as given and ask what would happen if a particular monopolist would try to find a better version of an existing technology. In a sense, we go back to Adam Smith. Okay, why the switch to factory system? Why the specialization of labor? Why mechanization? Okay. And as the name suggests, of course, these models have a very strong Schumpeterian logic, which is about creative destruction or creative accumulation. So there is a competitive sector, okay, that realize excess profit opportunities and act on these. So what is the downside of these models? We're going to discuss the scale effects problem next week. Other than the scale effect problem, the usual problems apply, right? So markets are, some markets are competitive, people know everything. So these models, in that larger sense, neoclassical models, because, they are general equilibrium models anyhow, right? So they must be counted as neoclassical. But these are the textbook versions. So for instance, if you look at the frontier literature, for instance, if you look at, growth papers published in top journals, models there are much more complicated and much more realistic. Most of the time, we cannot solve them by hand. Most of the time, we solve them using computers. We must be satisfied with the numerical solutions of the model. So that's it. That's how we can approach the Schumpeterian model from a methodological point of view. It is better. So think of this as a progress, right? So it is better than the Marshallian externality models. Why? Because now we can understand the purposeful decisions of these entrepreneurs. It is not good relative to the unified growth theory because these models can only explain growth. In the unified growth theory, you're going to see that we explain poverty and growth. Okay, so no model is realistic. Forget about this. If you want realistic models, you find a different universe where we have the tools and the mental capacities to write realistic models.
Okay, thank you.
All right. Any other? Okay, so I will post some readings as well. Maybe you can see what growth economists are publishing in these days, because the models I'm teaching you, I'm showing you, are a bit older. So the new literature, so you will see the newest literature towards the end of the semester. But let me put some readings on Schumpeterian models as well. Okay, so we're gonna meet over the weekend for the discussion of your proposals, and then we're gonna meet Wednesday for lecture 6 or lecture 5. I don't know. Okay. So bye-bye then. Thank you for showing up.
Thanks.
Thank
Thank you.
All right, bye-bye.
See you later.